We are online. So 25 slides, 25 minutes about plasma in the wild. My name is Johann, and I work on this project that is called LeapDAO. And we've been building a more VP, more viable plasma dialect over quite a long time, it feels. And in this talk, I want to share with you where we got and how it feels like to run it. But first, I guess I need to wake you up a little bit. So a show of hands, who knows plasma, or kind of, yeah, just raise your hand. Who would be kind of able to explain the difference between, let's say, plasma cache and plasma prime? 0 hands, okay. Oh, one guy, cool. That was half a vote. Yeah, let's get going. So I'll talk a bit about who. So who are these Leap peeps? And then what? So I'll give you a short rehearsal of plasma. How did it go to launch it on mainnet? That's what we've done beginning of February. And why? Why did we do that? So where are we going with this? Why another plasma? So yeah, let's go. So we started as kind of a bunch of game developers that really wanted to do something awesome on Ethereum, and we noticed that despite state channels and like all these kind of things, it was super hard to build decent games. And somehow through talking to the Ethereum Foundation and trying to do plasma research and all this kind of stuff, we ended up where we are. And instead of just being these freelance opportunists that we were at the beginning, we kind of evolved into something that, oh, I'm standing on the wrong corner here. Here's better. So we developed into this like community, and we got some values and stuff. So those are mostly like, running code. We don't have any hierarchies. There is no employment contracts. We don't even know the names of some of the members, and we try to achieve kind of rough consensus, no hard governance, hopefully no hard feelings. We had some disputes though along the way. And I don't know what that means, like market cap, but if there is a sort of value to the project, then we want to value the community over the value of the project in any decision. This is kind of where we are located every now and then. I think these are locations from GitHub or something like that, so they might not be accurate, but it's around about 5 to 10 guys that care about it. And this is kind of our HR everything board, so we just kind of operate on GitHub issues, and you can propose bounties, you can earn bounties, and there is nothing else than that. Okay, so the question was, because there was no microphone, if we're actively developing more VP or if we're just applying changes. I'll come to that later, but basically we've taken the more VP dialect and we've applied to it what the results of our research paper. So our objective is to get computation onto layer 2, so just do more than simple transfers. So we have not extended the more VP dialect with any specific attributes except those that are needed to run computation. So the assumptions of the exit game of more viable plasma, they stay the same. We haven't modified those. Okay, so I'll go through, there should be a plasma ball, but it's not showing up, just a few pixels. Yeah, I'll go through a rehearsal with you guys so you kind of know a little bit how plasma works, so I can talk about the other things. So this is kind of my mind map of scalability. It's a bit outdated, but the blue thing is Ethereum, and you can do different things like Casper and sharding and Ethereum 2.0 and so on to improve the scalability here, but it will only be a something X. And of course you can run other chains and bridge to them, but you always start with like a pretty low economic security. And you can do things that are like crypto economic games on top of layer 1, which is state channels, Plasma Cash. So if these two guys, Alice and Bob on the top right, they want to send 1 million transactions to each other, they can give it to the guy with a candle and pay probably a few $1,000s, or they can give it to this slightly less serious looking guy, the Plasma operator, and that guy will go ahead and hash it all together and then only commit 32 bytes into the Ethereum chain. So what he will actually do, he will put a number on it as well, so you can kind of identify that and put it into the Plasma contract. And what does that give us? So that gives us the ability to do proofs about the data structure. So with the Merkle tree, you have the proof of inclusion, and if you do 2 proofs of inclusion, for example, of transaction 1 and transaction 2, and the inputs in the UTXO sense of inputs, if these 2 inputs point to the same output, then obviously this is a double spend. And what do you gain from like proving a double spend? Well, you make this Plasma operator a restricted authority. So let's say he put down a stake before he became the Plasma operator, then this can be a proof of slashing him. So now, why is that more effective than, you know, just submitting the whole block? Well, because these proofs are way more efficient than posting the whole block. And yeah, the contract can then take the transaction and parse it and make conclusions based on the transaction. So beginning of February, 2nd of February, we took what we've developed and we've put it on the mainnet. And that's the biggest part of this talk, is just kind of letting you guys know which experience we collected, what were the difficulties, and so on. So let's go. First, you need to know how we kind of structure these commits to Ethereum. So the Plasma chain runs on Tendermint, and it does 2 to 4 second blocks. And then 32 of these blocks are taken and they are hashed together again in the Merkle tree into what we call a period. And then this period is, so the Merkle root of that period is submitted to the Ethereum chain. So you can kind of conclude from this diagram that that would happen every 1 to 2 minutes. So our theoretical capacity using that design, I'm stressing theoretical, is 4,000 transactions per block, 128,000 transactions per period, and then there's a governance parameter that says that the distance between 2 periods should be at least 6 mainnet blocks. So that's the period distance here, 1.5 minutes about. So with that, we could do 1,400 transactions per second. Cool. What have we actually done? Well, we've done 0.5 transactions per block, about 16 transactions per period, and the average distance was about 105 Ethereum blocks. So every 33 minutes in February, on average, there has been a period, and that gives you 0.008 transactions per second. So here is something that comes out of the Tendermint repository. Someone did a load test on Tendermint nodes. And it turns out that if you stress them with a little more than 1,200 transactions per second, their capacity actually decreases down to something at like 200 transactions per second at 6,000 transactions load. So let's take this point. Let's take like the theoretical capacity, as I said, was 1,000-something transactions, but let's just take these 200. So this is what we've actually measured. So the period submission cost 82,000 gas, and an average gas cost during that month was 5.3 gigabyte, pretty cheap. We've done 1,100 periods, and we've paid about $72 in that time. Well, what does that give us? A little bit more math. So on the mainnet, if you send a single transaction, let's just say it's a transfer, 21,000 gas, let's assume a pretty high gas cost of 20 gigabyte, and the ether price of $130, you end up with 5.5 cents. Correct me if I'm wrong. And then this is what we've achieved now on the Plasma chain, just doing stupid transfers, is 16 transactions per period, as I said. And then submitting that takes 82,000 gas, and we end up at 1.3 cents per Plasma transaction. So we've kind of done a 4x increase, even with like the very shitty load that we have. And now let's remember these 200 transactions that I've shown you in the load measurement. And if we would max out our capacity to that, then that would end up at a cost of 0.0012 cents per transaction. So being on Plasma, you're kind of a little bit cheaper than on the mainnet already, and there is a lot of room for improvement, but you need to kind of, there need to be enough transaction to do this stuff. So all this math, transactions per second, who cares about transfers, right? So it's cool to measure these things, but TPS is not really like, how do you say, the most important thing that we care about. We exist because we wanna bring decentralized apps to layer 2. So it's cool to roll up transactions and to process a lot of them, but with Ethereum we all kind of have this dream of doing more than just transfers, right? So certification, mediation of trust, all these kind of things. And so last year, with the help of our first Ethereum grant, we came up with this design that we call Plasma Leap, and the idea is basically to allow apps to kind of take this leap onto layer 2, and then they would become Plasma apps or PLAPs. And with this, there is like difficulties in doing that, but we think, as on the mainnet, developers need kind of stateful programming model to be able to develop these applications. And in the next few slides, I want to kind of take you through the difficulties that there are and how it's still possible to develop apps that run on layer 2. Cool. So the first thing that we did is go back to Bitcoin and look at pay-to-script hash, because that's how scripting or computation is done on Bitcoin. And if you remember, and let me see if I get that right. You take your redeem script, and then you hash that, and then you send funds to it. And it's redeemable if anyone is able to bring the redeem script that hashes to the hash that holds the funds, and some data that evaluates the redeem script to true. And the data usually contains the witness, so the signatures over the data, and so we've modeled off of that, and we call these things spending conditions, because coins are locked under these scripts, and you can release them by kind of bringing the contract and bringing the data that evaluates the contract to true. Bitcoin doesn't have any state, so you can't store anything between one pay-to-script hash and another one, and then use it in the next pay-to-script hash. And yeah, I'll talk about that on the next slide. So here's such a spending condition example. This is written in Solidity. It could be written in Viper. You have a bunch of constants, so there's the spender address, the guy that is able to claim from this. And then there's just a simple function, fulfill, and that takes the witness, so a signature, and then it also takes some instructions, like which token to send and where to send it to. And the script just recovers the signer from the signature, makes sure that that matches the constant that is saved in it. And then it initializes an ERC20 and tries a transfer. And if all that passes, then the spending condition has been fulfilled, and a UTXO that has been holding funds under this spending condition is spent on the Plasma chain, and the funds are transferred. So how do you actually make sure that all this happens correctly? Because we are not running on chain, and we don't know if the operator of this Plasma chain, remember this untrustworthy orange guy, if he actually is doing what he's supposed to do, right? So we are developing a component that is called SolEVM, Solidity EVM, and it's an implementation of the EVM inside of the EVM. And this component is there not to execute the full spending condition because, because it's kind of emulated, it would be way more expensive, and we would be limited to way less gas than we are on the mainnet. What it does, it plays an interactive game with the solver and the challenger, and then it only executes one opcode on chain. So this is very similar to what TrueBit does with WebAssembly, except that we use this for EVM bytecode. So you can write your contracts in any EVM language. And here's a simple example. So let's say I have a computation and I roll it out over all the opcodes. So the first opcode is, initializing the contract, and the last opcode is a return or a throw or whatever it might be, right? Then we have all these steps. And at each of these steps, I hash the state of the VM. And that means I take the memory and hash it together, I take the stack and hash it together, I take all the environment variables and hash it together, then I hash all that together, and then I get 32 bytes that represent the state of the VM at each of these steps. And then the interactive game between the solver and the challenger starts, and they kind of start and ask each other on chain, what is your state of the VM at step 7? And then they notice, oh, it's the same, so we must disagree somewhere in the second half of the execution. And then they do this binary search until they end up with 2 consecutive steps, so one after the other, where they agree on the first one, but they disagree on the second one. And this is where the EVM in the EVM steps in, and either one of them initializes the EVM. The EVM makes sure that after hashing itself, it matches the hash that is in this example, step 12, and then it executes that one opcode, and it sees who of these two guys was right in their claim of what the next step of execution is. And with this interactive game, we can make sure that, the computation that the Plasma operator uses to, for example, challenge exits, that this computation has been executed correctly. Let me check the time. Lots of time. Cool. Let's go. So, we don't have a stateful computing model yet, right? What do I mean by stateful? So just the fact that, I can use the storage of the contract. So you can just go to the top of your contract and you can say, like, I don't know, define a variable and change it later in another transaction, right? So unfortunately, state makes the exit game of Plasma so much more complicated, and we can't use it. So our smart contracts can just be like static scripts. And now you say like, oh, I can't really use that because I want to build state machines, right? I want to represent something that will do something else in a later transaction. And this was where we come up with an extension of fungible tokens, an extension of the ERC 721. Because the Plasma chain can manage 2 types of assets. The fungible tokens, that are used for transfers and gas and whatnot, and non-fungible tokens. So we just bring in a non-fungible token and we extend it with a 32 bytes data record. So imagine this as just changing the color of your CryptoKitty. And in the color of the CryptoKitty, you can now encode all kind of stuff. So always the current owner of this NFT can change the data, the storage root. And you would say like, yeah, well, but I'm limited to 32 bytes. How is this any useful for me? So, but you're not actually. You can do what is called state minimized storage. I think we could use that for Ethereum 1.x quite nicely as well. And here is an example of using a Patricia tree to kind of store more data in your token than just these 32 bytes. So you have a verify function here, which obviously takes a token ID, and it takes a key and a value, and a branch mask, and siblings as well. And with this data, we can prove that the current root includes a value at the key in this Patricia tree that is stored in the non-fungible storage token. So we verify the proof, and then we just return true. So you have to bring your own data, but you can verify during the execution that it is actually contained for reading, or you can bring an update proof as well, which is not included in this example, but if you check out our SoliVM and spending conditions repositories, you'll find it there. So finally, let's put it all together. On the left side, you see 2 squares, which are outputs of previous transactions. And then the 4 squares on the right are together a transaction with 2 inputs and 2 outputs. And the first input contains the spending condition. That is, for example, reading from a storage token. And the second input, it just points to the storage token that I want to read. This is kind of how we translate the UTXO model into the execution environment of your spending condition. And here, as you've seen before, you can just use the ERC20, ERC721 interfaces to talk to assets and storage and all this stuff that is around on the chain. And your contract is written in a way that, let's say there is a problem with the Plasma chain, it doesn't continue, or your user is just not happy with it and he decides that it should be exited, or you want to run your app on a faster chain, then you can exit your contract. So that means you deploy it on the mainnet. Then you call the Plasma exit functions, which will first exit the storage token, exit the assets that were in your contract, and then you have everything on Ethereum mainnet to continue running that contract, to invoking it again and, I don't know, transferring it into another Plasma chain, or just paying your users out or something like that. So yeah, that's it already. So check out our website. There's docs, there's the testnet, where you can run these spending conditions already. So we have these spending conditions on the testnet, not yet on the mainnet. On the mainnet, you can, for now, just run simple transfers. The moment that we got SoliVM completed, we will also launch these spending conditions on the mainnet, and then they will be fully enforced with this interactive game that I've shown you. Or write me an email right there at the bottom with questions that you can also ask now.
Can you open the slide with the pay-to-script hash Solidity version? I mean...
This one?
Yeah. What's the sort of... Okay, so there's like an output that has the hash of the script.
Yes.
And is this... This is
the script. So you take the script, you hash it, and you hash it first, and then you do a RIPE-MD 160 on it. So you get 20 bytes, right? It looks like an address. And then you just send money to that address. That's how you deploy a contract.
All right. So is it now kind of like this is the script that has been hashed before, and now it's comparing the hash of this script and checking that that's kind of correct? Because I mean, in some sense, when you recover the signer,
Yeah.
It could be just anyone who signed that script.
Yeah, what we do here, it's a little confusing because it's not really like commented, but you see how we try to recover the code hash from the address of this script. So the execution environment of the smart contract on the Plasma chain, we inject the SIG hash of the transaction as this, like as the address that you get when you would read this on the mainnet, right? So what happens is that you sign over the hash of the transaction, and then that gets injected into the contract, and the contract can verify against its own hash that you know the right person has signed it.
Sure, but I mean, in some sense, suppose somebody now sent the code hash, right?
It's not the code hash in this situation, though. It's the SIG hash of the transaction. So it's a hash over all inputs, all outputs. And because it hashes over the inputs, it also hashes over the transactions that will be spent, that we have on the chain before. So it acts as a nonce in this situation.
Okay. Yeah, I mean, what I was just thinking that can I now like get that bytecode, sign it myself, and then sort of like kind of become the signer in that thing? Because I mean, then it would recover my signature.
Yeah, but we have the address of the supposed spender hashed into this contract, right? Mm-hmm. So yeah, that would be hard for you. More questions? Cool. Thanks, guys. Come and ask questions.